Today we're going to go over combustion engines. This is one of my favorite lessons of the year. Whether or not you'll understand it by the end, I don't know. I think after 20 years of doing it, I think I'm barely getting it myself. So what I'd like you to do is in the packet, I'd like you to turn to the page of notes that says combustion engine. I want to talk through these notes quickly if we could. And then I have a video that my daughter Hannah and I shot on Saturday on how a combustion engine works. And then I've got a couple other clips, and maybe by the end of it, you'll get it. Probably in another 20 years. But I think you will get this, actually, today. So the combustion engine. This is the thing. This is pretty much the holy grail of the last 100 years. This and refrigeration. We have been able to take energy from the sun that has been stored as a fossil fuel for 1 million years, extract it from the ground, and stick it in an engine. That's crazy. But what's really crazy is that I can get 1 gallon of gas. Picture a gallon in your milk jug filled with gasoline, and I can get that to move my minivan 25 miles. The energy stored in that 1 gallon of gas. Now picture the amount of work it would take for me to push that minivan 25 miles. Yeah, that gives you an indication of how much energy we're talking about and how amazing it is that we can get combustion engines to do this work for us. So let's get right to it. One of the things about the first law of thermodynamics is we've got delta U equals Q plus W. Change in internal energy of the gas equals Q plus W. But where the heck does the heat come from? It could be in different processes. It could. However, one easy way to get heat is to ignite a mixture of oxygen and a fossil fuel. And then we get combustion. And when a combustion chemical reaction occurs, heat is released. So we can add heat to the gas by sparking a fuel and air mixture and change the internal energy of the gas and get it to do useful work. Combustion engines and much of our society is based on that very simple idea. So let's take a look at what a PV diagram for a combustion engine would actually look like. So as a reminder, the work done by a gas is the net area under the curve. And I should say when it's clockwise. I'll explain in a bit. When it comes to a combustion engine, the thing to remember is ICP. Intake, compression, power, exhaust. That is how a typical 4-stroke engine works. Bear with me. I know you'll get it. Let's go through the process using the diagram I have up above. We're going to start at point A. And we're first going to have an intake stroke where it pulls in a gas-air mixture till it reaches point B. Then from point B to point C, there is adiabatic compression. That happens so fast that no heat flows in and out of the system. Adiabatic compression. Now work is done on the gas and it heats up the gas and it increases in temperature. Now, at that instant, from C to D, this is actually not a stroke. This is when the spark plug fires from C to D. And when that happens, a whole bunch of heat is added to the system, but no work is done during that time because there's no change in the volume. So it's now at a higher isotherm. Then we have our power stroke. During the power stroke, the gas itself does work by expanding and pushing out. Then the valves open. And when the valve first opens, boom, the pressure drops. This again is not a stroke. This is like an instant. The exhaust valve opens, pressure drops, And then it exhausts, that's my red arrow here, back to point A. Intake, wait, hold on. Let's try that again. Ready, intake, compression, ignition, power stroke, exhaust, intake, compression, bam, power stroke, exhaust, intake, compression, bam, power stroke, exhaust. Does anyone have any clue what I'm talking about? I don't know if you do. So I thought what might help is if we took a look at, hold on. Let me grab this. I thought I'd play a little while this is going on. Ready? Here's a really nice animation for how a 4-stroke combustion engine works. This is actually diesel, so it's a little bit different. Doesn't have a spark plug. Roll with it. Ready? Did you guys get all that? No, you didn't. Holy cow. So here we have a cross-section cutaway of a piston. And if I look at the area in the middle, that's where the gas is going to be pulled in. Boy, that was a lot of information in 30 seconds. I'm going to play it again. Those are our valves right there up at the top. We see our oil down in the oil pan at the bottom. We have our coolant that circulates around on the outside so this piston doesn't get so hot that it melts. And the valves are really the key. Now the cam operators, or the cam shafts, these rotating parts up at the top, they're in blue above the intake and exhaust valves, are actually what get the timing of the whole system. The valves have to open up at just the right time. Let's see if I play this a little longer. So it's drawing in that air-gas mixture. Because this is a diesel engine, it's a little bit different. But in a regular gasoline engine, this would be an air and fuel mixture. And the fuel injector here would instead be the spark plug. So right here, the intake. That would be considered work done on the gas, and that's happening because if it has one piston in the system, there's a flywheel that has momentum that keeps things rolling. If it's a if it's a four-cylinder engine, then the other cylinders are also firing at the same time. So that, in combination with the flywheel, allows for this compression stroke. Again, that's because it was diesel that it's inserting the fuel there. Normally, if this was gas, that would be an air-gas mixture, and then, boom, what would happen is the spark plug would spark it, and now we'd have our power stroke. Heat is released to the system. The internal energy of the gas increases. And now it's going to push outwards and do useful work. There it is. There it is, the power stroke. That's what powers our economy right there. Keep it going. And there's our exhaust stroke. ICP. And then it starts all over again. Okay, so now that you can actually imagine what's going on with the piston, let's go back to our graph. ICP, intake, compression, power, exhaust. Intake, compression, power, exhaust. Ready? Intake, compression, spark, power, exhaust. There it is. Okay, so we've got an animation, we've got a graph. Think about what the processes are here. From process B, C, I can see that it's compression, and it's adiabatic because it happens so fast. There's no time for the heat to flow into the system, so the temperature increases. Next, we have C to D is isometric. The ignition of the gas increases the energy of the gas by raising the temperature, but it doesn't do any work on it or by it because it's not compressing or anything. And then the adiabatic expansion. This is the power stroke. The gas does work by expanding. The work done on the gas, therefore, would be negative because it expanded. Right? So here's just another visual. We have our intake, sucks it in, compression, compresses the gas, spark plug with both valves closed. This is not actually a stroke. This is just a moment in time, releases heat to the system, and then we get our power or expansion. We call it the ICP, so we say power stroke and then exhaust. Now, okay, that's just another visual. So where's a simple four-stroke engine that everybody has at their house? Well, most of us have a lawnmower at home, or you've seen a lawnmower, or you've been stuck pushing a lawnmower around. So what I thought I would do is explain using my lawnmower all of the different physics that's involved. So my daughter, Hannah, who's extremely patient, came outside with me today, and we videotaped a couple explanations. This is a little long. It will all tie together, I promise. Ready? So without further ado, here is me. So what we're going to work on today is I would like to explain thermodynamics and combustion engines using my old lawnmower. Here, this is my lawnmower that still works. It's a sweet Craftsman that I got from Sears, I don't know, 12 years ago. And if I give it a pull, It's a pull start. Don't be that impressed, it's just a lawnmower. But the amount of physics that is involved in a lawnmower is pretty impressive. So what I would like to do is to talk about all the physics involved using my old lawnmower motor. So we're gonna sort of pull this thing apart, it's already mostly apart, and look at all the different aspects that we now would understand because of physics. Real quick, before I start taking it apart, Hannah, I don't know if you can see this. So the orientation of this, there it is. We have our oil here. We have our pull string there. And what I want you to see is that down on the bottom, there is the part that would be connected to the blade. And the blade would be spinning in a lawnmower like this. Got it? All right. So Hannah, why don't you come on over beside me, and we'll start to look at all the different aspects of what's going on.
There.
There we go. All right. So what we're looking at here is how to start it. Okay. So you start it by doing physical work to the system and pulling on this string. And what that does is it causes the flywheel to rotate. Now this flywheel has a lot of rotational inertia and it spins as I pull. But I can't mow my lawn by pulling the cord over and over. So how the heck does this thing work? Well, if you notice, and if Hannah can zoom in, embedded in the edge of this flywheel, you'll see that there's some different colored pieces of metal. And if I actually put my, let's see, find something a little lighter. If I put my screwdriver there, it sticks. Why? Because it's magnetic. And what happens is, as I physically pull on the string and turn this, these magnetic pieces pass by my induction coil. Now we know electromagnetic induction, if a magnet changes the flux through that coil, we get an EMF induced. That creates a current that will pass. So that current then travels here, and this wire, maybe back up a little more, Hannah, is connected to this piece right here, which is located out in the front of your mower, and you'll see it, and some of you will recognize that that right there is your spark plug. If I unscrew it quickly, we can see that in a spark plug, there is a really small gap right there between these two leads. And when there's an electric current that flows, a spark will happen right there. Now that spark is used to ignite the gas. Now, a couple other really cool things to see about this flywheel. You'll notice that the flywheel, as it turns, there's a couple different spots. So right here, there's a magnet, and now there's nothing. And then as it turns a little more, there's now more of a magnetic field. And there's space such that I get it turns on, now it's off, on, off, on. So there's a cycle. We'll talk about that in a second. Now, so you know, this flywheel is attached all the way through to this bar down on the bottom. This is what the lawnmower blade attaches to, and this is where we get our useful work out of the system. So this setup sits right down on the lawnmower, boom, and that piece sticks out the bottom. Okay, so we've got electromagnetic induction. We have rotational inertia. What's next? Well, we've got a little bit of fluid dynamics here. Now this is falling off. In order to get combustion, what do you need? Now Hannah told me this because she had learned it the other day. You need what? Fuel, air, and spark. So we talked about the spark. That's the spark. Oh, it's called a spark plug. Air and fuel are actually drawn into the piston together. Now here, if I were to pull this apart quickly, I have my air filter. There's a hole there where the air is drawn into the carburetor. Now fuel comes into the carburetor and actually fills up this cup down on the bottom. So there's gas, and there's a little more to it, but right now we can say that there's gas in this cup. Now as air is drawn into the piston, and And Hannah, you're going to have to zoom in here. Maybe I'll hold it so you can see it nicely. As air is drawn in, it goes over that tiny little brass tube. Can you see that brass tube,
yeah.
Hannah? What happens is, as the air flows in, it pulls across that. Now, that's going to create low pressure just above that nozzle, and that's going to draw the fuel out and atomize it. A combustion engine uses a carburetor and Bernoulli's principle to atomize that fuel, so we have a really nice gas-air mixture. Now I take that piece off, and now I can see that the gas-air mixture comes in this tube, which looks like it's connected to over here. All right, now, what is the point of all this? Oh yeah, thermodynamics. This is where it gets interesting. Now this plate on the top, you can see that it's held together by, well, I don't know, 6 of these screws. Why is it held on so tight? Because it wants to explode. So this is what is holding it all together. Another thing you might notice is that these plates have these fins on them. The reason is this thing gets hot, and this will help dissipate some of the heat. You'll see this on a lot of devices. When you see fins like this, it's really you're trying to dissipate excess heat from the system. So, as I pull the screws out and take this part away, see where the spark plug is. See it? No, just maybe keep it there. Good. Oh, did I screw it up? Okay.
No, we're still good.
We're still good. As I pull it away, that spark plug is right there. So here I pull it away, and here's where the magic happens. This is my head gasket. This is something that when this goes in your car, it's really expensive to replace. I've had to do that on an old beat up used minivan once, and it stinks. But that is the head gasket. This is the piston, and here are the valves. And here's what I want you to see. I'm just going to turn this and watch what happens. I'm going to physically turn this. The piston goes up, goes down, up. Ooh, did you see a little motion there? Yeah, look at the piston is moving up and down, and the valves are opening and closing. So a combustion engine, a 4-stroke engine, has how many strokes to it, Hannah, do you think?
4.
Nice, yeah, 4. Good. So it has intake, compression, power, and exhaust. And let's see how that works. I'm going to start at the top. Fuel is pulled in here. Fuel and air comes through here, and it actually is back against this valve. As the wheel turns, the valve opens, and the piston sucks in fuel-air mixture. Intake. Then the valve closes. Now the momentum of the flywheel compresses the gas and air, and then, look up here, Hannah. See, we've got our magnets. They are going to, at just the right instant, induce a current, create a spark, and that spark is going to ignite the gas. When it does that, it allows for a huge amount of heat to be given to the system. So Q is added. During that time, the temperature is high, and the explosion of the gas causes the gas to expand, and it pushes against it. Pushes. This is the power stroke. That was the power stroke. Now, this valve opens up. This is the exhaust valve. And then during the return, the exhaust, it pushes all of the combusted gas out the valve. And then if you look, that valve is connected right to this thing, which is your muffler, which lets the excess heat and gases come out. So let's just watch the cycle. Intake, compression, power stroke, and then the exhaust. Intake, compression, that's the momentum of the flywheel and the lawnmower blade.
spark, power stroke, gas is expanding, exhaust. And it just goes over and over and over and over again. It doesn't have to think, it just does. Maybe 60 times a second, that system is happening. This is what's happening in your vehicle. Your vehicle, however, would have 4 or 6 pistons that are going to fire at slightly different times to keep the system rolling. And that's it. That is how now. You got to get this. You got to get this. We use combustion engines to take fossil fuels and convert it into useful work. This is it. This is the whole thing right here. In one little $200 lawnmower engine, this is how combustion engines work. This is how we get useful work out of chemical reactions. Intake, compression, power stroke, exhaust. There it is. Henny, do you think we got it? Do you have any questions? Any other questions out there? No? Good, because I probably don't have any other answers. I hope you guys are all good. If you could give Hannah a big round of applause for being our videographer today, I'd appreciate it. If you have more questions about lawnmowers, look it up online. There's a lot of smart people out there, much smarter than I am. Look it up, or go out in the shed, test it, and while you're at it, mow the lawn. Hope you guys are good. We'll talk more soon. Thanks. Bye.
All right, I think I'm going to stop there. I think I had a question and answer period where Josh had a moment to ask a question and a couple other people spoke up. But now that I'm watching it, I'm pretty sure I covered what I wanted to there. So I'm going to stop with that video and go back to our visual. A PV diagram explains this. Now, there are 2 last things I want to hit on this diagram that you should be wondering about. And that is the work done on the gas during the system and the work done by the gas. The gas was compressed during B to C. So from B to C, right here, the area under that curve would be the work done on the gas. And this is the key. From C to D, the temperature increased dramatically. Now, when that happened, we're up at a higher isotherm, and now the gas expanded. The work done by the gas from D to E, look at it. The area under that curve is much greater than the area under the curve BC. And the difference is going to be the area enclosed during that process. That is the work done by the gas.